Lesson 7, the correlation coefficient. Before you do this note sheet, make sure you have already completed this homework assignment, the correlation coefficient. So if you have not done that already, then pause the video and do that first. Okay, so let's refer to that assignment here first before we fill in our notes. So I'm going to go to that Desmos assignment, and this was the first slide. And the first question was, here are two scatter plots, explain how they are alike and how they are different. So you may have noticed they're alike, or they're different in that this one here, the points are all kind of accumulated. They're close to, very linear. They're close to a line. Whereas this one here, they're much more spread out. Right, so you might still have a line of best fit that's similar, like this, but the points are not gathered as closely. The data is not clustered around the line. But you may have noticed they're similar in that they both have downward slope. Like the line of best fit is a negative. Line of best fit has negative slope. Okay, and then we go to the next slide and we see 9 different scatter plots. And we learn a term. It says here, when the points on a scatter plot follow a line, we say there is a linear association between x and y. And here are some terms that describe linear association. So we can describe the strength of the linear association. So if we select weak, what happens is the highlighted, the ones that are visible here that are not faded out, those ones show weak linear association. So think about what those have in common with each other. Whereas these ones here, if I select strong, these ones show strong linear association. So think about what that means. How are these ones different than the ones that are weak? You may have noticed the ones that are strong, their data points are more clustered around what would be a line of best fit. Whereas weak correlation, they are more scattered across the graph. Now, how about direction? Here's ones that show a negative linear association. And then here are the ones that show a positive linear association. So you might look at these and think, what do they have in common? Well, the negative ones, if you drew the line of best fit for each of these, would have negative sloping lines. Meaning as x got bigger, the y value got smaller. Whereas these ones have positive sloping lines of best fit. And then finally you had this nice slide where you're able to adjust what's called the R value. So the R value is a number that describes both the strength and the direction of a linear association. It's what's called the correlation coefficient. So if we put it all the way at -1, we see points exactly in a line with a negative slope of the line of best fit. If we move it all the way to +1, we see lines exactly in a line with a positive slope. And then as we change it, if we go from +1, it's still here a positive, let's say like positive 0.8. It's still the line of best fit, if you were to draw it, would still be a positive slope, but the points are not as clustered towards each other. They are spread out a little more. And then if we go all the way to say 0, or -0.1, 0, there's no obvious line of best fit pattern, right? Like if we did a line, I guess it'd probably be a horizontal line, I suppose. Maybe there wouldn't even, I don't know. That would be interesting to look at. So they don't seem to be related or correlated at all, the x and the y values. Whereas now as we get more negative, closer to -1, and we move it, notice they're starting to cluster closer and closer to an actual line all along the line. So you'll write for that homework assignment, or you already did, what you noticed and wondered. So back to now we can fill in our note sheet. And This is from that, I took the same language from that assignment. When the points on a scatter plot follow a line, we say there's a linear association between the x value and the y value of each point. So in that exercise, we learned these two terms, the strength of the linear association and the direction. So pause this video and fill out these here, and then also these questions about direction. All right, coming back from your pause, let's see how you did. When the data is tightly clustered around a line of best fit, we say there's a strong linear relationship. When it's not tightly clustered, that would be weak. List the graphs below that show a strong correlation between x and y. So you may have said A, that shows a really strong correlation, right? F, very strong. And then some of these other ones are still pretty strong as well. B, I would say, C, are all strong linear associations. You might have even said D. D is pretty strong too. So A, B, C, and F. What do you notice about their R values? Well, let's pause a minute here on filling out this chart, and let's assign these R values before we fill in the rest of the chart. So we'll do process of elimination. So this one is all the way, this part 1A is all the way exactly on a line with a positive slope. So that would have an R value of 1. And so I'm going to cross that off. Which one would have the R value of -1? Well, it would be this one here, right? Because they're all on a line. So and they are in a negative association with each other. As x increases, y decreases, right, as you go along. So I would pause the video now and try to fill in the other, use these other R values, match them with the graphs. Okay, so let's see here. I'm going to do this one. This is very strong negative correlation. So what's the next strongest negative correlation? I would say that's probably C. And then maybe I'm going to do this one next. What's the next strongest positive correlation? I would say probably B. And then here's one. I'm going to do this one next. What is the weakest correlation? So this is close to 0, right? So that means it's going to really not look like it's on a clustered around a line at all. That would be, I think, this one. So it does have the computers will do a line of best fit. It just won't fit the data that well, right? Though you have lots of points all over that are not real close to that line. And then we have a -0.74. And let's see, we only have one other negative left, so it must be this one. We used that one. And then +0.48 and +0.65. So we have to decide between H and E, which shows a stronger linear correlation, and that will be the R value that's closer to +1. I think this is the stronger one, so that would be 0.65, and this would be 0.48. So now we're ready to go back and answer these questions. The R values with strong correlations those R values are close to either 1 or -1. It looks like a 2. Make that look more like a 1 here. A correlation coefficient with a value near +1 suggests a strong positive relationship. Let's try this. If a line of best fit has a positive slope, we say there is a positive relationship between the variables. For these graphs, as the value of x increases, the value of y also increases. The ones that show a positive correlation would be, let's see here, A, B, E, and H below. Their R values are all positive. If the correlation coefficient R is positive, the line of best fit has a positive slope. Okay, now let's do some practice on the back. You're going to fill this in. The closer the correlation coefficient is to 1 or -1, the more linear the data. And how correlated, or how the strength of correlation is different in different contexts. Like if you have, if you're doing precise physics with really precise instruments and you get a correlation coefficient of 0.8, that might not be considered that strong. But in something where you're like taking a survey of people, a correlation of 0.8 might be considered very strong. Okay, let's talk about how we fill out this chart. So for each of these situations, you're going to describe the strength and the relationship of linear association. And then you're going to give an explanation for why the variables might or might not be correlated. So the first one, number of steps taken per day and number of kilometers walked per day. So this R is is close to 1, so that is going to be a strong association. And it's positive, so it's going to be a positive linear association. And explain why this might be true. Let's think about this. When every time you take a step, it's going to increase how far you've walked each day. So it would make sense that as steps increase, distance traveled increases. Okay, let's do another one together. Here's one, you'll do this one on your own. Car weight and distance traveled using a full tank of gas. So we see the R here is negative. It's still a pretty big number, it's close to -1, so I would say this is still a strong association, and it's a negative relationship. And let's see, so this means that this is the weight of the car, and this is how far it can get on a tank of gas. So as a car gets, so here's a car that's not very heavy. We might put a data point here. It can get pretty far on a tank of gas. Here's a car that's a little heavier. It might not get quite as far. A really heavy car up here might really not go very far at all on a full tank of gas. But it's not quite as strong as the other ones, right? Because a tank is different sizes. Like those big cars actually can get far, they have bigger tanks, right? So it might be, you might get a stronger correlation if it was miles per gallon or something. But to explain, you might say heavier cars are less fuel efficient. Okay, so let's maybe do one more here. Let's look at one that is not very correlated. This R value is close to 0, so that would be a weak and negative. Average time spent listening to music per day and average time spent watching TV per day. So it looks like that's not very correlated. So people who listen to a lot of music don't necessarily watch a lot of TV, or they don't watch less TV. So you might say something like time watching TV is unrelated to time listening to music, which is not correlated. Okay, you will do the rest on your own, and you'll get credit for them.